So let's change our focus from a straight wire to a loop of wire. We'll focus here on a square loop of wire because it's easier to analyze than if we had a circular loop or any other shape. But the same idea that we'll talk about can apply to any loop of wire, any current carrying loop of wire, that is. So since a wire that's in a magnetic field with a current flowing through it could possibly experience a magnetic force, if we have a loop, we could actually get that loop to turn because it may experience a torque. So I have an example on the screen here of a square loop. Now you may be wondering, how do we get a current in a closed loop if there's nothing else in that loop? So usually in our loop we have pieces that come out and connect to something else, like you see of these top two pieces right here. So those would be connected to something else that would make a current go into the loop, and you can see that this current is going counterclockwise in this case. And so what we'll do is we'll analyze each straight segment of wire to see what torque or what force it experiences. Starting with that segment that's on the left that has the lowercase letter a next to it, if I use the right hand rule, I would find that the magnetic force on that segment of wire is pointed out. And so I'm going to put a little dot right here to represent that force. That bottom part of the wire that has the lowercase letter b next to it, so this bottom part right here, it's, first of all, it's not really in the field from the drawing here, but even if it were in the field, the current would be parallel to the magnetic field, which means it would not experience a force, because we know that the cross product, if the two vectors are parallel to each other, there is no force. And so then we'll focus on this upward portion, the portion that's on the right hand side with the upward current. And if I do the right hand rule there, I'll find that the force is pointed in. And so I have an inward force there. So if I look at a top view of my wire loop, then we'll see the directions of those two forces. And if you think of ignoring this, you don't have to worry about this black vector right here that has mu on it. But if I think about what would happen if I have an object like this with these two forces, it would start to spin. This would have a torque on it. Now, thinking back to what we've learned about torque, it's been a while since we've thought about it, but we know that torque is equal to R cross F. And so we could find the torque on this loop by doing the radius crossed with the net magnetic force. So it's really important that you want to pay attention to. It's the net magnetic force in this case. Or you could do the torque on each segment and then find the net torque. Actually, take it back. Don't use the net magnetic force. You'll end up getting 0. Find the net torque instead. So we'll focus on the torque on the left-hand side and then the torque on the right-hand side, and then you could add those two torques together. When I would be doing radius, I'd be looking at the distance from the axis of rotation, which in my side view picture is marked as a dashed line. And so it would be that distance to where the force is applied. So if I were looking at the left wire where the current is going downward, the R in that case would be half of B. We'll of course get lots of practice using this idea as well.